So good morning all of you. Here in this video I am going to discuss about the Biot-Savart's law. Okay. So this is just similar to the Coulomb's law in electrostatics. So we know that we studied in our electrostatics about the properties of charges when charges are at rest, which gives about the information stationary charges. Stationary charges. So these stationary charges produce constant electric field. Constant electric field. And this constant electric field, to understand the properties of this constant electric field, we call it as electrostatics. Here in our magnetostatics, we study about the steady current. Here, the Biot-Savart's law helps to understand the properties of the steady current. So, the steady current will produce a magnetic field which is constant. So, constant magnetic field. Constant magnetic field. And to study the properties of this constant magnetic field, we call it as magnetostatics. So magnetostatics, which gives the information about the steady current and constant magnetic field. Okay, this electrostatic gives the information about the constant electric field and stationary charges. So there we study the properties of charges when charges are at rest, how to add, so how to multiply. Okay, so what are the properties of these charges? If two like charges are if two charges are like charges, then what are these properties? If two different charges are coming near, so what will be the effect? So what will be the effect of what will be the electrostatic field produced by these charges? How to calculate the force of attraction or repulsion between the two forces, how it varies with respect to distance. So what is the potential, what is the field produced by these charges at somewhere distance r. So multipole expansion, so dipole moment, the field produced by this dipole moment. So these are all we studied in our electrostatics. Okay, so the energy for also continuous charge distributions, discrete charge distributions, these are all we studied in our electrostatics. Here in magnetostatics, so we are going to calculate the magnetic field and magnetic force which is produced by this steady current. And also if you place this steady current wire in an external magnetic field, so what is the force on this steady current? Okay, so this is all we will study in our magnetostatics. So this Biot-Savart's law give some information to understand the properties of this steady current and the field produced by this steady current. He gives some equation. So let us see. Okay, so the Biot-Savart's law help to understand the properties of steady current which produce a magnetic field, right? So let us take a small wire of this is a small wire which carries a current I. Let us take a small length element dl, current element. So this current per unit length of a wire. Okay, so this is steady current I which is moving in a wire. So this steady current is nothing but current per unit length is same, constant. The current per unit length is constant. So here if you take this current per unit length, here also constant. If you take current length element here also current is constant. So this current is not varying with respect to time. Okay, the current entering this per unit length here is also equal to the current leaving per unit length here. Okay, so current per unit length of a wire is always constant. So this type of current we call it as steady current. It does not vary with respect to time. Okay, so this steady current will also produce a magnetic field. So we are going to calculate the magnetic field, how this magnetic field varies, how this magnetic field affect due to this current wire. Okay, so let us take a small length element dl. So according to Biot-Savart, he observed that this dB is directly proportional to the length element current I and dl. If suppose here I am going to calculate the magnetic field at a point P, distance r, this r is the position vector from the point where you are calculating the magnetic field and current element dl. Okay, okay, this is my dl length element. If suppose it makes an angle theta, this point where you are calculating the magnetic field which makes an angle theta with length element, this current element dl. So next, this magnetic field here, it also depends on theta, it depends on sin theta. Okay, this magnetic field also depends on theta which makes angle dl with the position vector r. Okay, so next, and also dB is inversely proportional to 1 by r square. So if we move further from this current source, our magnetic field also decreases inversely like this. So it depends on theta means, suppose this is our current carrying wire, if we calculate here the magnetic field is different. Okay, this is my length element dl, this is position vector r. If we calculate here, theta will different and our magnetic field is also different. If we calculate here, our theta is also different and our magnetic field also decreases, it's also different. If we calculate magnetic field here, our r is different, so magnetic field is also different. If we calculate here, so r is different, so our magnetic field is also different. So magnetic field is also decreases with increasing the distance. It varies like this, and it depends on magnitude of I. If the magnitude of I is more, current, the magnetic field produced by this moving current is also more. Okay, if the magnitude of this current, this steady current is decreases, the magnetic field produced by this current is also decreases. Okay, so overall we can write like this: dB is directly proportional to I dl sin theta divided by r square. dB is directly proportional to I dl sin theta divided by r square, and we can write proportionality constant dB is equal to mu naught divided by 4 pi into I dl sin theta divided by r square. Okay, and this proportionality constant mu naught divided by 4 pi is a proportionality constant, and this mu naught is permeability of free space. That means the free space which allows the magnetic field to pass through it, how much it permit to allow the magnetic field to pass through it. So if the permeability is more, the magnetic field there also more, that means more magnetic field will pass through that surface. Okay, so next, the value of this mu naught is 4 pi into 10 to the power of minus 7 Newton. Okay, so Newton per ampere square. So see, in our electrostatics, electric field E is equal to 1 by 4 pi epsilon naught into Q divided by R square. So this is also similar to our magnetostatics field or magnetic field. So there source is our charges, these are stationary charge is our source in electrostatics. Okay, so here our source is IDL. Their electric field is also inversely varies as R square. Here our magnetic field inversely varies as R square. Okay, and this mu naught there, see, in electrostatics, electric field is inversely proportional to 1 by epsilon naught. But here our magnetic field dB is directly proportional to the mu naught. There our permittivity will oppose the electrostatic field to pass through it. It does not easily allow. If permittivity is more, electric field lines pass through it to is decreases. Okay, it resists to flow, but here our permeability allows the magnetic field to pass through it. Okay, so here dB is directly proportional to the mu naught. Okay. Okay, next, so the total magnetic field B, if we integrate all these line elements, okay, so all these current elements, if we integrate all these current elements, so then we will get the total magnetic field B, which is equal to mu naught divided by 4 pi with we are integrating with their respective limits, so integration I dl sin theta divided by r square. So in vector form we can write this as B is equal to mu naught I divided by 4 pi integration dl cross r cap divided by r square. So this is the expression for Biot-Savart's law. This is the expression given by Biot-Savart's law to understand the properties of magnetic field which are produced by this steady current. Okay.